Class, good morning. So again, this is the third presentation in power cycle. So by this time, I will give you the actual Rankine cycle. Okay. So actual Rankine cycle. So this is class again, the illustration of the Rankine cycle. Okay. Next, so we have here the assumption. So the presence of the following conditions will transform the ideal cycle into actual one. So previously, we used the ideal cycle. Okay. So first, we have here the pressure drop in the steam generator. Okay. So if there is class of pressure drop in the boiler, so of course the process is now actual one. Okay. So another is pressure drop in the steam line. Okay. Pressure drop in the condenser. Pressure drop in the feed water line. So heat losses in the steam line. Okay. So heat losses in the turbine or the engine, reversible adiabatic expansion in the turbine. So meaning it is no longer isentropic. Another is the inefficient pump. Okay. Another is subcooled condensate. Okay. So that is class the assumption. Okay. Another, so the illustration are all the same. Okay, so the heat added again is h sub 1, okay, minus h sub 4 prime. So h sub 4 prime is the final enthalpy at the uh, boiler pressure rather, okay, at the boiler pressure. And the heat rejected class is the h2 prime minus h3 prime, okay. So we consider the final, okay. So this is not the original enthalpy. So the original is h sub 2. Okay. So since the expansion is no longer isentropic, so if you look at the TS diagram, so the line or the curve from 1 to 2 is no longer a straight downward. Okay. And for h sub 3, the enthalpy of course is not, the enthalpy of the liquid is not uh, based on the pressure at the condenser. Okay. So another is the engine work. Okay. So you study this class. Huh? Okay. So if you study this, you can easily identify, of course, the difference between the cycles. Okay. Another is the engine work. So we have here the reversible adiabatic expansion. Okay. So that is from 1 to 2. So take note, this is no longer isentropic. This is polytropic. Okay. Okay, W is equals to h sub 1 prime minus h sub 2 prime. Or polytropic expansion from 1 prime to 2 prime, or energy in equals to energy out. H sub 1 prime minus equals to h sub 2 prime plus W plus the loss, of course. So based on the illustration. Okay. So the heat loss, of course, inside the turbine. Okay. So another class, we have the pump work. So pump work is W sub P prime is the ideal pump work divided by the mechanical efficiency. So this is the efficiency of the pump class. So it is now included. So but in ideal, we do not consider the mechanical efficiency of the pump and other losses, of course, in the steam and the liquid lines. Okay. So another, we have here the actual cycle thermal efficiency. So we have here the work prime minus the pump work prime over the heat added prime. Okay. QA. So that is thermal efficiency. Okay. So another, here we have the actual Rankine engine. Okay. So if during the expansion process, the steam undergoes a process other than isentropic, the engine is said to be an actual one. Okay? So again, for the heat added, Q equals to h sub 1 minus h sub 2 prime. Take note, class, we are only considering the engine. It's either uh, steam engine or the steam turbine. Okay? So, this is class engine. Rankine engine. Okay? So, energy chargeable against the engine. So, that is h sub 1 prime minus h sub F3 prime. Okay? For the thermal efficiency, so that is the W sub prime, and then energy chargeable prime equals to h sub 1 prime minus h sub 2 prime minus h sub 1 minus h sub 3 prime. Okay, so this is class almost similar to the previous discussion, okay, or the previous presentation rather. So we have here some definition of terms, okay. So we have turbo generator, so a generator driven by a turbine. Ideal work, so the work done by the steam during a reversible adiabatic expansion process in the turbine. Take note, class, reversible, okay? Meaning isentropic expansion, okay? Indicated or actual fluid work, so the work done by the steam during an irreversible adiabatic expansion. Adiabatic class, not adiabatics, okay? So typographical error. Okay? So, or polytropic expansion process in the turbine. Another is the brake work. Okay, so we have here, brake work is a useful work. Okay, and then combined work is electrical energy available at the generator. Okay. So, another class we have here, thermal efficiency. So, ideal thermal efficiency. So, that is the work divided by the energy chargeable. Indicated thermal efficiency is the indicated work divided by thermal efficiency, or the energy chargeable rather. Brake thermal, so we have here the brake work over the energy chargeable. And the combined thermal efficiency is the combined work over the energy chargeable. Take note, class, that the thermal efficiency E for ideal is greater than the thermal efficiency indicated, greater than thermal efficiency brake, and then greater than the combined thermal efficiency. Okay? So another, we have steam rates. So ideal steam rates. So that is M 3600 over W of the work. The indicated steam rates, MI equals to 3600 over D. W sub I, take note, class. So this is just the reciprocal of the previous presentation, or the thermal efficiency rather. Okay. So okay, this is similar. Okay. Indicated steam rates, MI, 3,600 over W sub I. Brake steam rates, MB, 3,600 over W sub B. And then combined steam rates, 3,600 over work combined. And then engine efficiencies, okay? So the indicated engine efficiency is equals to indicated work in okay, over W. Brake engine efficiency is the brake work over W. Combined engine efficiency is the combined work over the W. And then the turbine engine mechanical efficiencies is of course the brake work over the indicated work. And for the generator efficiency, that is the combined work over the brake work. Okay? So, another is heat rate class. Okay? So, if you study the presentation of the equation, so this is very similar class to each other. Okay? So, for the ideal heat rate, HR equals to M of multiplied by the energy chargeable. Indicated heat rate, HRI or MI times energy chargeable. And then brake heat rate, MB, and then multiplied by the energy chargeable. Combined heat rate is the okay, HRK MK multiplied by EC. Okay, so thank you very much, class. So next presentation will be the example class of the formulas presented in these three presentations. Okay, so thank you very much, class.